This is a brief introduction into working with data that really is level shift data. Fundamentally, what you have are an excursion of the value that you've been getting from one place to the other. And what one really wants to do is define the excursion region, define the zeros for both x and y of the excursions, define the bounds, use tangent to reveal the general trends, and then use derivative to reveal details of the whole excursion. So here the points are in order. Well, let's first plot x, y, then reset the zeros for x and y, then calculate the slope, then co-plot slope and xy data, and interpret the results. Let's go through this now. Here's a set of data that is not zeroed because the transducers weren't zeroed. So go through the original data file and find out what the zero value should be, and manipulate the raw data file and store a new data file with the zero corrected values. You'll see that it didn't change the character of the data at all. It simply changed the numbers where they start and stop. Take the derivative of the zero corrected data now, which is y2 minus y1 divided by x2 minus x1, and plot that. And you'll notice it has a lot of scatter at the far end and a little bit of noise at the front and a sort of lump in the 2/3 of the way through the data set. Now when you co-plot that to the original xy data, you find out that the slope is really telling you there's a maximum slope of the blue line, and it's about halfway up the excursion. And in fact, if you look at the peak of the derivative, that's going to give you the maximum slope of the xy plot. There you can see it on the screen. The next thing you do is you look at the maximum excursion of the raw xy plot. And then you turn around and want to do some interpretation, and you say, oh my goodness, there are a bunch of different portions of the plot. There's a touchdown region, very little at very low values. Then there's a region where you have a particularly low slope, and then there's a region, a main region, where a lot of things are going on and there's a lot of force being added and significant displacement. And then finally there's a failure region where the sample is changing irreversibly. So you can look at this particular collection of data as just touchdown is really uninformative except to find out where zero is. Then there's a minor mechanism region initially, which could be the sample changing shape to conform with the supports, or it could be that you have a sample with two very different materials together, and this is compressing the one material before the main material. Then you have the elastic deformation region. Then you finally start to see a little bit of plastic deformation where the slope now decreases at the far right-hand side of plastic 1. And then you see a significant decrease in the values, and that'll be irreversible deformation of the sample. Now, interestingly, a lot of software treat data like this significantly differently, and you can find any kind of numbers from A to B to C, or C minus A, or C minus B, or A minus B. And so it's worthwhile to characterize your software carefully when you go about making measurements and making sense of samples. The most important first thing, though, is getting a good graphics tool to start the whole process of understanding.